All right, PostGIS 3 came out 2 weeks or so after Postgres 12. We always try to release our releases more or less in sync with Postgres. And yeah, so people are making a big deal about it because it's the number. The number changed. It went from 2 to 3. And people make a big deal about that, and that's fair because, you know, we've only had the 3 numbers. Actually, no, zero base, we've actually had 4. So it's worth kind of going back and saying, so why did the big number change in the past? So back in the day, the first releases of PostGIS were all 0.x releases. So actually the first major version number was 0. The first release was 0.1. You got a geometry type, you got an index on that type, and you got a distance function. That was it. That was PostGIS 0.1. And sadly enough, that was about 80% of the functionality most people want of a spatial database. It's just like, I want to stick my geometry in, I want to get it back really fast, and every once in a while I want to know how far apart things are. That's good, you're done. So that's enough functionality to support web mapping software like Map Server. That was the first client ever for PostGIS that drew a picture. So 0.x implementations, they were simple, brutal. We're just trying to see if it would work. Because, you know, we started off using Postgres and like we didn't know. We just knew we wanted a spatial database. And the question was, what's the best way to do this? Well, Postgres says it does type extension. Let's try. And the result was, in terms of storage structures, pretty heavy. Every feature on disk was stored with 3 dimensions, even if it only had 2. Every feature on disk was stored with a full double precision 3-dimensional bounding box. Didn't matter what type the function was. I think they all had srids embedded as well. Net, it took a lot of space to store even very small things like a point. So points are 2 coordinates. Each coordinate is stored in double precision, and double precision numbers are 8 bytes. So a point in a platonic ideal world should take 16 bytes. That's it. Anything above 16 bytes is overhead. The 0.x version of PostGIS took 81 bytes. So it was really heavyweight. But it was useful. It did the things we want. It put things fast in and out. We used it for our government projects, like I said, roads and watersheds. It worked good. So what was 1.x? I was encouraged vociferously by a member of the open source community, Arnold Crystal, to just release 1.0. He was running a consulting company in Germany at the time. Because installing 0.x software freaks out my customers. So that seemed valid. So we wanted to up the number just to sort of indicate that we'd done a lot of stuff. And in fairness, we had, between 0.1 and 1.0, we had added full support for the simple features for SQL specification. And we had largely rewritten or fully rewritten the disk storage format and swung the pendulum 100% in the other direction. So 1.x used what was called the lightweight storage format. All the metadata information about the stuff on disk was stored in a single byte at the front of the object. So as a result, we could store a point, a simple 2-dimensional point with no boxes, no srids, in 17 bytes. We were only 1 byte above platonic perfection. And that's as good as it gets if you have a variable-sized object. So that was as good as it got. It was really, really good. The reason we made things smaller is because as we're doing these projects with watersheds and roads, and we found that big things are slow. When you have to move around a lot of data to do stuff, it slows things down. So the smaller amount of data you can push through your CPU, through your memory, through your I/O bus, and still represent the same logical thing, the better. So we made things lightweight. That was good. It was very good. But for PostGIS 2, so PostGIS 1 was when? 2005? Anyways, PostGIS 2, quite a number of years on, 2009-ish. So at that point we had another 5 years of experience. And over 5 years, the functional base of the project got a lot bigger. And all the metadata for everything about the object had to be stored in 1 byte. At the end of the 1.x era, we had no more space to add additional types. We only had 4 bits to encode the type. We'd used up all those bits. There was no space for new types. One of the trade-offs, the developer, Dave of the 1.0 serialization, I did the 2.0 serialization. One of the trade-offs he made was I can make things faster if I shove all the data up to the front of the object. For the programmers in the room, that meant the doubles all became unaligned. That meant that in order to read any of the data and do math on it, you had to copy it from where it was sitting in memory over to an aligned memory address. So everything that worked with the geometry involved step 1, read it off disk, step 2, copy everything to an aligned space, step 3, do stuff. So we had this sort of built-in CPU overhead. So 2.x did two things. It gave us more metadata space so we could continue expanding and adding functionality to the extension. And 2, it aligned all the coordinates so that we could do direct access, come off disk, read the data directly. So it speeded up a whole bunch of operations, basically any operation where we weren't going to be rewriting the geometry and just straight up reading it. And that's most of them, got faster. Each time we did this, each time we changed the on-disk format, it meant that when someone was upgrading from 0.x to 1.x or from 1.x to 2.x, the software which read things off disk no longer understood the bytes which were sitting on disk from the previous version. So every upgrade forced users to go through a dump and restore. So if you're going to go from 0.x to 1.x, you dumped your database, you installed 1.x, you restored your database. This is fine for people who are working with personal projects. This is fine for people who are working with 50 megabytes of data, 100 megabytes of data. People who are running extremely large production databases really get angry with you when you tell them that in order to upgrade, they're going to have to A, turn off your database, B, dump it all out into a dump file, which is a text format and therefore very large, and the dump has to run, it doesn't run in parallel, and then restore it all. So if you're dealing with 1 terabyte, 10 terabyte data sets, these people were not happy with that. And we kept doing it to them because it was good for this project. And 2.x was a while ago. And 2.x got us all the way up to here. And once again, 2.x had the same problem as 3.x. We used up all of our header space again. We had no more space to add additional functionality. So we needed to reorganize the header so we can add more space for flags, so we can tell the system that we're adding new funny features. So 3.x, one of the reasons we have a major version number is that we have changed the on-disk format again. That is actually not the bad news you would think it is, given what I just said. 3.x does not require a dump and restore because the format for 2.x included 2 bits of version information. So we have both copies of the code still in place. We have the 2.x copy of the code and we have the 3.x copy of the code. And the system looks and sees the version information. Oh, I'm reading 2.x bytes here. I will use the 2.x reader. And I'm writing, I will write 3.x format. So basically, you can upgrade your software, and it will transparently continue to read the old versions of the format. And when you write new data down, it will transparently write the new version of the format. So it's not a dump and restore upgrade to go from 2 to 3. So we have lost that major piece of backwards incompatibility. But it is still a change in the format. And that's one of the reasons why we bumped it up. We still have the same approximate overhead for geometry storage that we did with 2.x, which is a little higher than the 1.x version, but not too bad, about 30% worse than the 1.x version. That is retained in 3.x, but because we've added this extra space for feature flagging, we now have the possibility of doing things like building a lightweight point storage type. Maybe that'll come in 3.1, which allows us to squeeze about 30% off point storage, which is the only case where the overhead really is noticeable anyways. So we'll probably take a run at that for 3.1 and make point storage much more efficient. So we've been PostGIS versions come in 3 valued versions, major, minor, patch. So this is 3.0.0. We follow what's called the semantic versioning scheme. So that means when the big number changes, you can expect backward breaking changes. We try to document them all. For 2 to 3, there's not a lot of them, as opposed to, say, from 1 to 2, where there were quite a lot. The minor version is a flag for, hey, there's been new features added. We do a minor version release about once a year in the same cycle as Postgres. And then the patch version, the third one, means we've made things better, but we have not changed the functionality of the system at all. All the functions should give you the same outputs, given the same inputs. Mostly it's bug fixes. Every once in a while, if there's like a really good performance improvement that doesn't involve a lot of code change, we'll slide a performance improvement into a patch release, as long as it doesn't change behavior and as long as it's not so big that we're afraid we'll break things. But that's what the major minor patch versions mean. going forward. And that's been how it's in the past, and that's how it'll be in the future. So it took us about 10 years to go from 2.x to 3.x. It'll probably take us another 10 years to go from 3.x to 4.x. And we have another version flag left, so we're still not going to require a dump and restore when that happens. So what are the major changes in 3, other than changing the on-disk format? First of all, for sysadmins, semi-big deal. Once upon a time, from the instantiation of Raster in 2.0 until now, when you typed create extension PostGIS, you got all of the vector format functions, all the things that deal with points, lines, and polygons. You also got all the raster format functions, all the functions that dealt with raster chips. People who've been packaging PostGIS find that that adds a very large dependency chain, and folks who want to package a later version of PostGIS say, is there some way we could get the rasters out and make them optional? So we've broken it out. As of PostGIS 3, create extension PostGIS gets you all the vector form functions. If you want the raster form functions, you do create extension PostGIS raster. They always had independent linking libraries, but create extension PostGIS drew them both in. So this neatly separates things. So one linking library per extension. Raster depends on the core, and then the rest of the extensions are more or less the same, except we've made the SF-SQL extension, which depends on the fancy SF-SQL computational geometry library, fully independent, whereas before it was partially independent. So everything should be packaged much more cleanly. So from the point of view of system administrators, it means if your users are going to be using Raster, they have to explicitly enable it now. It has some implications for upgrades. Most people won't notice that because your system administrators will do this for you. But if you're upgrading from 2.5 to 3.x, it's a multi-stepper. First, you're going to run the alter extension update, which is just as before. What it will do is it'll update all the vector functions to the new extension. But unfortunately, it's impossible to repackage a second extension while you're upgrading a first one. So what we do is we update the vector stuff, and we unbundle all the raster stuff. And it's just lying there like a bunch of chips on the floor. And then as a second step, we remind people with that hint, hey, run this spare function, the PostGIS extensions upgrade function. And what that does is it finds all the chips on the floor, which are the remaining raster pieces, and bundles them up into a PostGIS raster extension. So at the end of that step, you have both of the new extensions. Your old database has been upgraded from 2 to 3, and you'd have both a PostGIS extension and a PostGIS raster extension. It's just something to look out for if you're used to doing the 2.4 to 2.5 update. There's one extra step, just this one time for the 2 to 3 update. Under the covers, again, system administrators will like this. This is mostly for packagers and people who have to automate updates. We used to push around PostGIS library with major minor versioning. This meant that in the midst of an upgrade step, you briefly get a state where your database was running. Because it would have SQL bindings for the old version that pointed to, that failed to point to a new version of the library, which is what the software had installed. By backing it out once, we're only carrying around the major version. The interim step now is fully operational, so you won't have this sort of moment where things are running. This should make things like doing PC upgrades and non-dump and store upgrades far more reliable. It's something that mostly packagers care about, but as end users of packagers, you will care about it too, because your upgrade should be much more clear and straightforward. I already talked about the on-disk format. Not much more to say because nothing has happened in terms of new performance. We've just added flags and not used them, so it won't be until PostGIS 3.1 that we start reaping the benefits of that. There'll be some spatial functionality that make things faster, and there'll be this idea of lightweight point in a minute. This is the big one. This is the one that it is unbelievably obscure. First of all, I gotta say, it is unbelievably obscure and it's hard to explain, but I'm going to give it a try. In PostGIS 2, in fact, all the way back to the beginning of time, the SF-SQL functions like ST-intersects, ST-contains, ST-within, you want these functions to run fast. And to run fast, they have to get into the index. And the only way Postgres recognizes that your query involves the index is if there's an operator as part of the query. So the spatial index operator is this ampersand operator. So what we did all the way up until 2.5 was when you called ST-intersects, we just quietly under the covers rewrote it to be select object, operator object, and then do an exact test of the intersection. So what that effectively did was it used the index to sieve out all the things which couldn't possibly fulfill the condition, and then used the exact test underbar ST intersects to sieve out things which didn't fulfill the condition. That worked great for a long time. It's sort of inherently understandable. Unfortunately, it was confusing to the Postgres planner. It made the Postgres planner find it hard to figure out what the underlying costs of things were, which had this knock-on effect that parallel queries, or queries you would want to be parallel using spatial functions, didn't parallelize. So even though since Postgres 10 there's been a pretty decent and robust parallel query mechanism inside Postgres, if you ran PostGIS functions, you would not see parallelism popping up the way you wanted, not until you got into cases like tens of millions of rows that the ordinary planning mechanism said, oh, they should be parallel. We want to parallelize much sooner in the spatial domain because our functions are way more computationally intensive. But the only way we can make that happen is if we can notify the planner by declaring very large costs on our functions. But the planner couldn't recognize the costs, we were screwed. In Postgres 12, Tom Lane, my colleague at Crunchy, added an unbelievably obscure API, which he called a support function. It does like a half dozen things, but we used it for one thing only. We used it for a native function binding. So note that the PostGIS 3 binding for ST intersects does not do this unwrapping, this rewriting trick anymore. It just goes straight into the C library. And we use Tom's support function API to quietly stick the index operator into the front. So we still get an indexed query. So everything's still really fast. But because the function is defined in complex, the cost is right at the top, floats up. The planner recognizes that's parallelizing. And we've had users who've taken Postgres 12, Postgres 3, and started running workloads on it. And they've seen exactly what you expect. Run a 32-bar machine, we start to see performance go up very, very rapidly. So I used the test that I did on a somewhat smaller machine, I think a 16-way machine. This is a flat linear summarization. Starting from 1 core and looking at 16 cores. You can see it's not a linear improvement, which is too bad. There's overheads in doing things parallel, so it doesn't just go up to 1/16th of the time. But it does keep going down. The more you add CPUs, the faster it gets. And even better, I gotta say, to the point of view of, wow, I'm so impressed by the Postgres community. The planner, the star there is where the planner, the number of workers the planner chose, which is more or less right where the cost benefit starts to change, where the curve inflects. So I mean, yeah, I got all the points by forcing the system to execute more simply. You can always force it if you want to. But the planner just on its own will get the place where it's kind of the dividing line where so we can truly want to get better. This kind of paralyzed in the old days. This did not paralyze at all prior to Postgres 12. You could not get a spatial query. You had to cut off your hand and do various occult things to get it to happen. And even that didn't work very well. This one worked hard. Yeah, but took no changes, none of this involves any custom tuning. This is running default settings. We recognized that we needed a parallel plan and parallelized it with 50 cores that made sense. Given the inflection point of the result. It's really, really good. So if you want things to go faster, get a nice big node. And you find the parallel queries now go much faster. It makes use of Postgres 12's parallelization system. It's fabulous. There's been a bunch of smaller changes as well. I talked to you about Prod 6. Change supporting the new API for Prod. That means you get all the benefits of the new Prod, which is now being actively developed by professional geodesists. And they're doing crazy stuff that only geodesists understand. But it's important to do because our data are changing, sometimes slowly, sometimes quickly, as in that case. Stuff moves, and you want to make sure that the data is matched up and changed between GeoAs with the least precision reduction possible. That's what the new project allows us to do. Also, updated data work. Crunchy data team, me and Michael Davis spent a lot of time on this cycle. Not direct work on PostGIS, but it has improved PostGIS a lot because we have GeoAs. We have made it more proper with C++ data. We have got a whole bunch of improvements just around profiling to strip out bad interpretation practices. We brought in some new algorithms from the core JTS library, algorithm development, and net is that some functions like point on the surface are 10 times faster. Generally, constructing geometry functions, things like and so on, are about 28 faster. That's just implementation changes. So really, really happy with GIS 3.0. People are using map vector tiles and VP vector tiles. Big improvements there in performance. This is a big deal if you're generating tiles right from the database. And talk later about doing that. I think it's a really cool way to generate tiles. Real companies with real production problems around generating tiles have moved towards doing their tile generation from the database as opposed to pulling the data out and doing tile generation in the middleware. They find that it's faster, they find that they're getting correct results, and that thins out their application as well. Just like NVT, we've enhanced the GeoJSON support. Back in the old days, we've had GeoJSON support for a really long time. And I don't believe I'm wrong in saying that GeoJSON is perhaps the stupidest possible structure for handling attributes. Actually, no, I'm sure they're stupid. It's just lazy structure. So GeoJSON's spec specifies three things. It specifies how to represent a geometry in JSON, and we've supported that. It specifies how to represent a feature in JSON and how to represent a collection in JSON. And this is sort of like a standard table database. It's got an attribute, a name, it's got the geometry in it. You would think if you're going to represent this in JSON, a reasonable way to do it would be to use the JSON dictionary, where you've got a name attribute, and a geometry attribute, and a geometry. And maybe if you're in, we'll tend to have a type attribute to tell you that it's a feature. And that would be it. That is actually what the Postgres row JSON output is, if you run it on that table. It makes a great deal of sense. Sadly, it is not the specification. The specification is this. It's a dictionary, it's got a type, it's got a geometry, but instead of having the attributes from the table, they're nested under this thing, this properties dictionary. So we can't use the default JSON generator in Postgres. We need our own generator for our special GIS features. It's very a GIS forward thought model of how to handle a feature. Like in the GIS world, all features have geometry and they might have properties. No, that's not true. All objects have properties, and some of those properties might be geometry. But in GIS world, geometry is always there and it's very important. So that's why GeoJSON looks like it does. So we've added an STL to GeoJSON. It takes in a row parameter. The man who wrote it is right there, Joe Conley. Thank you, Joe. And people love it. It's a great way to generate GeoJSON and pass it straight back to your web apps, again, thinning out that middleware piece. I mentioned order by in 2.x, Z order in 3.x, Hilbert order. You can see spatial integrity is a little tighter there. Also, the algorithm we used for calculating it got about 20 to 30% faster. So if you're sorting on geometry, that's nice. And then because it's 3, we took advantage of the fact that we're backward breaking. And we dropped some functions we didn't like anymore. And mostly the functions that people didn't like anyways or use anyways. We had an accumulation function, which has been around forever, but Postgres did array-ag, and we shouldn't have ours anymore. We got rid of some of these silly signatures that have versions at the front of them that no one uses anyhow. And we broke out the SF Seagull stuff, which previously involved a silly little back-end switch, but now are only available if you turn on SF Seagull. So, every time you tell some people about what's involved in the current version, and we've now flipped over, I can't talk about what's coming in PostGIS 3.0 anymore because it came. So people always ask, so what about the next version? What are you going to do for us tomorrow? So here's what I can do for you tomorrow. And take this with a cube of salt. As I mentioned, with the improvements in the 3.0 serialization, we can start adding features again that take advantage of the serialization. Accelerated spatial join is one of those things. We've got improvements to Postgres 12 that are required. I've now got the improvements to PostGIS 3 that are required. I can finally do this project that's been sitting on my desk for about 5 years. So I'm going to do that, accelerated spatial join. We really want to get into more analytics. We feel that surface building and doing analytics of surfaces is a thing that people who are doing GIS workflows, and we want people to do GIS without the GIS, will find useful. So the ability to build surfaces, Krieg surfaces for things like temperatures, weighted surfaces for things like heat mappy style things, and then taking those surfaces and doing things like interpolating contour lines or isopolygons off of them. Makes a lot of sense, and people get a lot of use out of that. And then under the covers, we're going to do a lot of development work on GIS. Finish off robust overlay, add some geometry cleaning functions. The Harris guy should be very happy about that. And then add deterministic precision reduction. So you can force your data into a precision grid, but without losing geometry validity in the process. It is something which sounds very easy, but is unbelievably technically hard. That's it. I managed to do that in, well, I didn't go over. And yeah, so back to Adam, unless anyone has any questions first. All right. Thanks, man. Oh. Once again, if you want the deck, the URL's there. So that's the URL to the deck.